in many of the problems that we've been tackling, what we found is that one of the important ingredients in the solution to our problem is the Gramian of a matrix. And the Gramian of any matrix is a real symmetric matrix if the original matrix had real entries, and a Hermitian matrix if the original matrix had complex entries that weren't necessarily real. The spectral theorem is a theorem that allows us to conveniently factor any real symmetric matrix, or more generally any Hermitian matrix, by looking closely at the eigenvalues and eigenspaces of that matrix. So let's start by looking at an example that I think highlights the importance of the theorem. So here we have the data of two different 2x2 matrices called A and S. This first matrix A has two different eigenspaces. The first eigenspace corresponds to lambda equals 2, and the dimension here is 1, and the 1 basis vector is 2, negative 1. The second eigenspace corresponds to lambda equals negative 3, and the dimension of this space is also 1, and the single basis vector here is 1, negative 1. So A has two eigenspaces where the eigenvalues are 2 and negative 3. For lambda equals 2, the eigenspace is spanned by the single vector 2, negative 1. And for lambda equals negative 3, the space is spanned by the single vector 1, negative 1. The matrix S is a different matrix, although it's still 2x2. And this matrix S has the same eigenvalues as A. The eigenvalues are 2 and negative 3, and the dimension of the eigenspace for lambda equals 2 of S is 1, and that space is spanned by the single vector 2, negative 1. And the eigenspace for lambda equals negative 3 is also one-dimensional, with basis vector 1, negative 2. So at first glance, these two matrices have a lot in common, although they're definitely different. They're both 2x2 matrices, and they both have the same eigenvalues. Each matrix has the eigenvalues 2 and negative 3. And the geometric multiplicities of these eigenvalues are the same. They're both equal to 1. Or the eigenspaces each have dimension 1 for both of these matrices. They are, however, different matrices. The columns of A are 7, negative 5, 10, negative 8. And the columns of S are 1, 2, and 2 and negative 2. And the eigenvectors that we've chosen for our bases are different than from each other. So for lambda equals 2 as an eigenspace of A, we're looking at the basis vector 2, negative 1. And for the eigenspace of S, where lambda equals 2, our basis vector is 2, 1. And for lambda equals negative 3, the eigenspace of A is spanned by 1, negative 1. And for lambda equals negative 3, the eigenspace of S is spanned by 1, negative 2. So we have two matrices that have some things in common, but they are definitely different matrices. I want to look at a little bit closer at the eigenspaces. So here the eigenvalues are the same, but the eigenspaces are different. For for A, the two eigenvectors we have as our bases are 2, negative 1 and 1, negative 1. If we were to plot the spans of those vectors, we would be looking at two different lines in space. So one of these lines is spanned by 2, negative 1, which would be this line in red here. And the other would be 1, negative 1, which would be this line in blue. And one thing that I just want to point out for this example is that the two eigenspaces of A are not orthogonal to each other because these two basis vectors do not dot to 0. What do they dot to? 2 times 1 is 2, plus negative 1 times negative 1 is 1, 2 plus 1 is 3. So the eigenspaces of A are not orthogonal. Let's look at the eigenspaces of S. The eigenspaces of S are spanned by 2, 1, which would be this line in red, and then 1, negative 2, which would be this line in blue. These eigenspaces are orthogonal to one another because the dot product of 2, 1 with 1, negative 2 is 2 minus 2 equals 0. So the eigenvalues of these two matrices are the same, But the matrix A has eigenspaces that are not orthogonal to each other, and the eigenspaces of S are orthogonal to one another. Well, why might this be the case? One thing I'd like to point out is that the matrix S that we're working with here is a Hermitian matrix. Remember, Hermitian is a generalization of the notion of being symmetric. The conjugate transpose of S is equal to itself. On the other hand, this matrix A is not Hermitian. The conjugate transpose of A is not equal to A. So what I'm trying to illustrate with this one example is that here we have the data of a non-Hermitian matrix and a Hermitian matrix. These two matrices have the same eigenvalues, but the structure of the eigenspaces are very different. For the non-Hermitian matrix, the eigenspaces were not orthogonal, and for the Hermitian matrix, the eigenspaces are orthogonal. So this is symptomatic of the spectral theorem. The spectral theorem is a theorem that describes the eigenspaces of Hermitian matrices. Now, let's remind ourselves what Hermitian means. We say that a matrix S is Hermitian if its conjugate transpose is equal to itself. So, for example, each one of these three matrices is a Hermitian matrix. Our first matrix here is a 2 by 2 matrix. And notice that this matrix has all real entries, and it is symmetric. So this is an example of a real symmetric matrix, and real symmetric matrices are always Hermitian. This second matrix is a 3 by 3 real matrix, and if we compare entries across the diagonal, this negative 31 matches with this negative 31, this negative 44 matches with this negative 44, and negative 8 matches with negative 8. So we have all real entries with symmetry about the diagonal. This is another real symmetric matrix, and real symmetric matrices are always Hermitian. This third matrix has some complex entries that are not real. And if we compare across the diagonal, we no longer are guaranteed equalities because negative 3i plus 1 is different from 3i plus 1. However, these two numbers are related by conjugation. The conjugate of negative 3i plus 1 is 3i plus 1. The conjugate of negative I is plus I. And the conjugate of 4 is equal to 4. So this last matrix is not a symmetric matrix, but it is a Hermitian matrix because the conjugate transpose of this matrix is equal to itself.